All right, let's get started. Share my screen. Welcome to Chapter 30 of Physics with Philander University. We're going to be discussing quantum physics. How fun. As I said with the previous chapter, Chapter 29 on relativity, this topic is, to say it's much more expansive than we're going to cover is a joke. This topic is incredibly uh, difficult to understand, and given the math requirements for this particular physics class, we're going to go over the skimmest of skims. So, as I said previously, the last chapter, just make sure to look, if you decide to look into deeper sources on this material, make sure the proper sources. That's my only real gripe with this. There's a lot of people out there that throw around these words without a proper knowledge of them, or without even a somewhat comprehensible knowledge of them, and you end up getting a lot of baloney and hooky. So let's go over this very quickly. In quantum, we're going to discuss blackbody radiation and Planck's hypothesis of quantized energy, photons and the photoelectric effect, the mass momentum of a photon scattering, and the Compton effect. Then the Broglie, I don't know if I pronounced that correctly, I apologize, hypothesis and wave-particle duality, the Heisenberg uncertainty principle, and finally quantum tunneling. Yes, this stuff is all way above everyone's head. We're going to have some fun here. So, black body radiation. So when I say black body, what do I mean? Well, a black body is something that's shown here, wherein light enters it, bounces around, slowly loses energy, and is completely absorbed. As you know, the color black is the color that absorbs all light, correct? So a black body object would be something that absorbs all the energy. Once something goes into it, it doesn't come back out. That's the basic idea of a black body. And something we notice, if we look at these graphs here, an ideal black body is also an ideal energy radiator. If we measure the intensity of the electromagnetic radiation emitted by an ideal black body, so this is just the math of it, we find these graphs shown here on the side. And what we notice is the top graph has a 3000 Kelvin and 6000 Kelvin black body objects. And we notice that the intensity of the peak of the object is at different points. For example, at 3000, you're dealing in the infrared spectrum, but if you get up to a temperature of 6000, the black body radiator appears in the top of the infrared close to the red section. And then if you double that again to 12,000 Kelvin, which is right a stupidly hot temperature, you're getting into the violet purple range of peaking here. So what this means is the distribution of energy in a black body radiation is independent of the material from which the black body is constructed. It depends only on temperature. So if you see an object and can figure out its temperature, that tells you something about the black body radiation that you are discussing here. And since this temperature correlates very well to the frequency, or essentially the color of the object, black body, black referring again to absorbing energy, not necessarily the color black. If you think about it this way, you can notice that the temperature of an object relates directly to its peak frequency, as shown here, Wien's displacement law, which is a ridiculous constant times t. Meaning the peak frequency increases linearly with the temperature. This means the temperature of the black body can be determined by its color. Cool. Well, I was just saying. Classical physics calculations were completely unable to produce this temperature dependency, leading to something that was then called the ultraviolet catastrophe, as shown here. According to classical physics, as you increase the frequency, you increase intensity and just shoot straight to the moon. Again, when we get into modern physics, we realize that at certain scales, really small, really large, really hot, really cold, what have you, classical physics breaks down, and we need to get into more nuance with modern physics, such as Planck's hypothesis of quantized energy. Planck discovered that he could reproduce the experimental curve by assuming that the radiation in a black body came in quantized energy packets, depending on frequency. Energy packets being the interesting idea here, right? So if we take this energy and quantize it, which is, it seems as though they're just throwing quantum into everything, and it's kind of true. If you take the energy that you're discussing and you cut it down into distinct integers, 0, 1, 2, 3, you can pull out a relationship between the energy and the frequency. And the energy and the frequency are related to each other via Planck's constant down here below, 6.63 times 10 to the negative third joules per second. This constant, Planck's constant, relates the energy, E, on the left of that equation to the frequency, F, on the right of the equation, based on distinct packets, like little chunks of energy. Planck's constant is a very thin number. It's teeny, right? This means that the quantization of the energy of blackbody radiation is essentially imperceptible in most macroscopic situations. Again, this is what I've been talking about for a while here, wherein if you have a very small, very large, very hot, very cold situation beyond the normal scope of day-to-day life, classical physics has an issue with it. So we need to get more fancy with our math in order to properly rectify these things. It was, however, a most unsatisfactory solution, as it kind of appeared to make no sense. You know, this little teeny number relating this math to reality. That's where Einstein comes in with the photoelectric effect. Einstein suggested that the quantization of light was in fact real. That light came in small packets that we call photons of energy. So, right, we've been talking about light as a wave. Now we're talking about light as a packet of energy. An energy of a photon given a certain frequency is shown as this equation here. Energy is equal to H of course being Planck's constant, times the frequency. Therefore, a more intense beam of light will contain more photons, but the energy of each photon, in fact, does not change. So this goes back to Planck's equation where you had the integers, right? So a low intensity versus a high intensity beam of light is simply having more photons being shot out of it, even though they could, for example, be the same color. The photoelectric effect occurs when a beam of light strikes a metal, electrons are ejected. Each metal has a minimal amount of energy required to eject an electron. This is going a bit into chemistry now as well, so hopefully you've taken chemistry before this class, so this makes a bit of sense, called the work function, W naught. If the electron is given an energy E by the beam of light, its maximum kinetic energy is shown here. The energy that the beam had, subtract the work function out of it, and you get the max kinetic energy allowed of the beam. This cartoon here kind of shows this effect, right? So you have light coming in, hitting this set emitter. The light is breaking the electrons off the emitter, and those photoelectrons are shooting over to the collector, and then you plug this all into a circuit, and you can measure a voltage, current. An ammeter measures current, you can measure a current through this process as those electrons, because what is electricity, right? Moving of electrons, as those electrons move from emitter to collector via the light. So what do we have here? We have some classical predictions. Any beam of light of any color can eject electrons if it is intense enough. And then the maximum kinetic energy of an ejected electron increase as energy increases. What we observe is that light must have a certain minimum frequency in order to eject those electrons. And more intensity results in more electrons of the same amount of energy. So it's not necessarily that the energy is increasing, it's that there's more packets of the same amount of energy. Sort of a potato-potato thing going on here, right? But there is a distinct difference there. It's not that I have more energy being released, it's that I have more chunks of the same amount of energy. I'm not shooting the bow harder, I'm shooting more arrows. Explanation. Each photon's energy is determined by its frequency. If it is less than the work function, the electron won't be released no matter how intense the beam. Shown here as a cutoff frequency, that work W naught over H, the Planck's constant, gives you a cutoff frequency. So what this implies, what this tells us, is that these electrons don't just fall off given the intensity of the light. Has to do with the energy packets and the frequency of the light as well, the color of the light, if you will. And it says light here, but this works for most any radiation. A more intense beam means more photons, and therefore more ejected electrons. As we can see here, the maximum kinetic energy Kmax on the Y scale, and the cutoff frequency is the frequency on the X scale. What we notice is sodium and gold have very distinct bars, right? It's not a nice curve up as we go. Sodium has a specific cutoff frequency where it starts to release said electrons. Gold is a cutoff frequency where it starts to release electrons, and then the slope is given by Planck's constant. So Planck did some math back in the day, found this number that seems to allow him to reproduce these charts, and then later on Einstein and his theories allowed us to show, in fact, that his number was correct. So this is an example of really wonky math ending up being true because the math allowed us to get there. Photons always travel the speed of light, right, because they're light. What does this tell us about the mass and momentum? Well, since photons are moving, they have an energy, a kinetic energy, therefore they must have a mass and momentum, right? The total energy of a photon is shown here in this kind of gross-looking equation. What fun. Notice C, the speed of light, everywhere. Since the left side of the equation must be 0 for a photon, it follows that the right side must be 0 as well, because photons are, well, they're massless, but they have a momentum. A momentum needs a mass. It's all very confusing, right? So the rest mass of a photon we call 0. But the momentum of a photon can be written as this way. So dividing the momentum by the energy and substituting, we find the momentum is equal to E divided by C. Interesting. So something is massless but still has momentum. Finally, we can write the momentum of a photon in the following way. The momentum is equal to Planck's constant times the frequency divided by the speed of light, or Planck's constant divided by lambda, which is the wavelength of the light. So the photon has momentum, but doesn't have mass when it's not moving, but momentum has a mass to it. If you're confused, I understand. Again, my suggestion, I'm not going to be able to cover this stuff as in depth in this particular text as you may want. Find a reputable source, look into it deeper yourself. That is my suggestion to you. So let's continue. Photon scattering and the Compton effect. More fun stuff here. The Compton effect occurs when a photon scatters off an atomic electron. A photon hits an electron. What happens there? Well, it's got momentum. The electron is an object. They're going to bounce off each other, right? When this happens, the incident photon bounces off in some direction here shown as theta, and then the electron bounces off here shown at phi. So it's pool balls here, right? But in order for the energy to be conserved, the energy of the scattered photon plus the energy of the electron must equal the energy of the incoming photon, right? We talked about this in classical physics last semester. You can't gain energy somehow. This means the wavelength of the outgoing photon is longer than the wavelength of the incoming photon, since some of the energy was used up, right? This is what's known as a Compton shift, where your delta lambda, shown there, is given by that big, gross, nasty-looking equation. In 1923, de Broglie, I'm probably mispronouncing that, I'm sorry, proposed that as waves can exhibit particle-like behavior, particles should exhibit wave-like behavior as well. This is sounding familiar. He proposed that the same relationship between wavelength and momentum should apply to massive particles as well as photons. So what these scientists in the 20s were arguing is, if something's happening over here, and I'm seeing a very similar looking thing over there, what's happening over here might be happening over there, or reality is consistent. And he gave us a wavelength equation shown down here where lambda is equal to, lambda the wavelength is equal to h Planck's constant divided by p. So the correctness of this assumption has been verified many times over. One way is by observing diffraction. We talked about diffraction with light. Now we're talking about diffraction with particles. We already know that X-rays can diffract from crystal planes, as shown here, right? Your incident beam, your reflective beam, all this should sound familiar. Interesting enough, the same particle can be observed using either particles or X-rays. So if we shoot rays, X-rays at a crystal, we get the same result as if we shot particles at it. Indeed, we can even perform Young's two-slit experiment with particles of the appropriate wavelength and find the same diffraction pattern. So we know from a couple chapters ago, these diffraction patterns occur with light because light acts like a wave, right? We talked about water hitting breakers, waves scattering around, constructive, destructive interference to give us these light and dark bands. Funny enough, you shoot particles, they do the same thing, which you think wouldn't make sense, right? But this is the reality of the situation. This is even true if we have a particle beam so weak that only one particle is present at a time. We still see the diffraction pattern produced by constructive destructive interference. Also, as the diffraction pattern builds, we cannot predict where the particular particle will land, although we can predict the final appearance of the pattern. So that's kind of weird, right? Shown here is a whole bunch of arrows coming at this two-slit experiment producing this light and dark band. Well, if you erase all those arrows and just have one arrow there, the light and dark bands still appear, as shown here. These images show the gradual creation of electron diffraction pattern. And I don't know the particulars of these actual images, but what's being explained to you is that if these are lots of particles, waves, one particle, one wave, it doesn't matter. They all produce the same basic branching of constructive destructive interference. The uncertainty just mentioned, that we cannot know where any individual electron will hit the screen, is inherent to quantum physics and is due to wavelength property of matter. So even though we know what the answers, even though we know what's going to be made at the end of the experiment, I can't take a snapshot, can't take a picture mid-experiment and Sharpie out the electron is here at this particular moment. That's the Heisenberg uncertainty principle in a nutshell, sort of. So we know we have a central maxima, again, where the electron flows through this slit. Then we have dark fringes top and bottom, and we can figure out the angles causing these fringes and these central maxima to be made. Here, your delta py, delta npx, and of course your theta. The width of the central maxima is given by the wavelength of what you're shooting, theta, etc. Therefore, it would be possible to have a more narrow central peak by using light of a shorter wavelength, right? Because that's gonna, if you decrease lambda, you decrease theta. However, from the de Broglie relationship, sorry about that, as the wavelength goes down, the momentum goes up. As you show on your wavelength, you increase your momentum. So, when electrons diffract through the slit, they acquire a y component of momentum that they had not had before. This is, in fact, what leads to the uncertainty principle. So what we're saying here is, I know I shoot the electron before it hits the slit. However, once the electron or electrons go through W, shown here on the left, go through W, they get some delta py momentum, which causes them to give us a constructive central maximum or destructive dark fringe. If we know the position of the particle with greater precision, its momentum is more uncertain. If we know the momentum of the particle with greater precision, its position is more uncertain. Because how these two equations relate to each other, for example, greater px you have, the less theta you have, and back and forth. Mathematically, we have this gross looking equation here, wherein if we, for example, have a small delta y and a large momentum, we get one shape where there's a whole lot of uncertainty as to where the maxima is, because it's a very thick bell curve there, right? So a lot of stuff appearing. But if we decrease the momentum and increase the delta y, we have a thinner bell curve, so we have more likely to know where things are landing. Again, the relationship you need to look at here is the shape of that bell curve. No, think about what you know about bell curves, right? The shape of that bell curve, and then the momentum and the y involved. Wonky, right? The more you know about something, the less you know about other parts of it. I know where that car is, but I don't know how fast it's going. Or I know how fast the car is going, but I don't know where it is. The uncertainty principle can be cast in terms of energy and time rather than position and momentum if you want. As shown here, it's a variation of the same equation. The effects of the uncertainty principle are generally not noticed at macroscopic situations due to the smallness of Planck's constant. Again, all this stuff we're talking about doesn't technically matter in your day-to-day life. We're talking about individual subatomic particles at this point, going through stupidly tiny holes and being read on these incredibly tiny bands of light and dark constructive destructive interference. This isn't going to affect how the water goes in your glass. You know, this is quantum physics we're talking about here. So now that you have a complete understanding of quantum to this point, let's talk quantum tunneling. Waves, so now we're back to waves and particles. Waves can tunnel through narrow gaps of material that they otherwise would not be able to traverse. As the gap widens, the intensity of the transmitted wave decreases exponentially. So on A, we have a total internal reflection, the two fiber optic, if you will, it's just bouncing through. But if we include B here, a light tunnel across the gaps, we notice that there's some reflection and some refraction through the gap. Given their wave-like properties, it's not surprising that particles can tunnel as well, right? Because are they particles? Are they waves? Is light quantized packets of photons? Or is light a wave with a frequency and a wavelength? It's both, right? Or is it neither? You don't know. It's uncertain. A practical application is the scanning tunneling microscope, which can image single atoms using the tunneling of electrons. So, as you can see here, you have the microscope coming down. Electrons tunnel across this gap, showing the atomic surface, to give us interesting results. If you want, you can look more into it. It's up to you. Do what you want. But let's summarize this ridiculous journey we've taken together. So to start, an ideal black body absorbs all light incident on it, or all light connecting with it, right? The idea of black absorbs all is the absorption of all colors. The distribution of energy within it as a function of frequency depends only on its temperature. So if you look at a black body object, you can tell how much energy it has given by its temperature. Here are some equations for radiation relating to that. Come down here to Planck's constant, which is everywhere along with the speed of light in this quantum conversation. You can think of light as both photons, quantized packets of energy, and as wavelengths. And the interaction between radiation as photon radiation as a wave gives us many different attributes, such as the photoelectric effect, work functions, what have you. Then you have to take this idea of wave being a packet of energy and light being a packet of energy and light being a wave, and you have to figure out what to do about mass, because light has a momentum to it, but photons don't have masses. So you can have the quantum effect coming in. And finally, you can go over uncertainty principle, wherein since you don't know if light has a mass, light does not have a mass, but light has a momentum, and you don't know what light is. If you know its momentum, and if you don't know its momentum, then you kind of do know where it is because it's a wave, but it's the same time a particle. That's quantum for you. I hope it was confusing. I know it was confusing. And thanks for listening in. If you got any questions, leave them down below. My suggestion to you, as always, if this stuff is of interest to you, seek out more information from a reputable source. That's your best bet. Truth be told, and stay safe out there.